Okay, so we are going to start a new section, direct products. On several occasions in group theory, we have had the need to produce new groups from some given groups in different ways. One instance of this was in the 8th section, where we used automorphisms of groups to produce new groups. And if you remember, that new group turned out to always be abelian, and the dihedral groups turned out to be a special case of that kind of construction. However, so far we haven't made any attempt to do this kind of things systematically. It was somewhat ad hoc. Say, once we use automorphisms to create new groups, once we use something else by some other means we create new group. And those kind of constructions are somewhat, I won't say artificial, but somewhat quite complicated. They are not natural, that's what I want to say. But direct products are also some such constructions which are absolutely natural. So we will be given some groups, finitely many groups actually, where the number of groups can be anything, but it's finite. And we will form something called their direct products. And we will see that this construction is very simple and very natural. So let's see how it goes. Instead of considering the finite case right away, let us first see the case where we have only two groups. So let A and B be groups. So what we want to do is we want to consider the Cartesian product of A and B. Consider the set G equal to A times B. Of course, this is a non-empty set because A and B are both non-empty. And why is that so? Because A and B themselves are groups. Now, on this set, we are going to define a binary operation in the most natural way possible by defining it component wise. And by that we mean simply this. For any two elements which in this set are going to be ordered pairs, in G, we define their product to be this ordered pair. Where A1, A2 is the product of A1 and A2 in the group A. So in the group A, you would calculate the product A1, A2. Because A1 and A2 are elements of A, this is again going to be an element in A. And B1, B2 is the product of B1 and B2 in B. So this B1, B2 is going to be an element in capital B. And that means that this ordered pair is again going to be an element in G. Moreover, note one more thing, that for given A1 and A2, A1, A2 is a unique element in capital A. That's because the binary operation in the group A is well defined. So every time we take two elements of A, form their product, we are going to get a unique element in A. Similarly, for given B1 and B2, B1, B2 is a unique element in capital B. So this is a unique ordered pair or a unique element in capital G, and that makes this binary operation well defined. We however won't write this much. We will simply write clearly this operation is well defined. And within this statement that this operation is well defined is also contained the fact that G is closed under this operation. Okay, that's because it's well defined. So anytime you take two such ordered pairs and form their product using this definition, you are going to get again an ordered pair in G, well defined. And we however do mention that G is, although there is no need, see, the moment you say that a binary operation is there on some set, it automatically means that the set is closed under it. G is closed under it. So you can see that this definition is extremely natural. I mean, this is the simplest way one could imagine an operation that can be thought of in this setup, on this set, which is a Cartesian product. For any, okay, so next, in order to verify that this operation turns G into a group, we have to verify the other three axioms. We need to verify that this operation is associative, there exists an identity element, and every element in G has an inverse in G. So let us take these things one by one. A2, B2 and A3, B3 in G. You will notice that because this definition of the operation is very natural, so verification of all the axioms are also going to be absolutely straightforward. We calculate this product A1, B1, A2, B2, A3, B3. This will be A1, A2, B1, B2, A3, B3. A1, A2, A3, B1, B2, B3. And now you can apply the fact that, you can use the fact that the operations on A and B are both associative. Usually this kind of verification is left to the reader, to the student, but let's just go through it, why not? So using the fact that the operation on A is, capital A is associative, this product, this first component can be also written like this, A1, A2, A3. So now you understand why we were calling this product that we have defined it component wise, because the multiplication is component wise, that's why. Similarly, for that other product also, it can be written like this, and then this is equal to A1, B1, A2, A3, B2, B3. A2, B2 times A3, B3. So the above operation on G is associative. See, we do not use any symbol for a group operation in order to minimize writing effort. But when you verify this kind of things, because of a lack of symbol, you have to again and again say above operation, but that is only one time. Once you have the operation, once you have done all the verification, that's it. Then you can continue to use it without using any symbol for the operation. Next comes identity element. That is rather easy. Let E in A and F in B be identity elements. I mean, both of these are groups, so each one of them will have its own identity. For A, we are denoting it by E, like what we usually do, but for B, in order to distinguish it from E, we just write F. Some people would like to write something like this, retaining that E symbol and writing like this. EA would denote the identity in A and EB would denote the identity in B. But we stick to E and F because in the text the author has done so. Identity elements. Then this ordered pair belongs to G such that for any element A comma B in G, we are going to see that this E comma F is going to behave like an identity, which almost you can see immediately. BF, because E is the identity in capital A and F is the identity in capital B. So this is just A and B, and that can also be written as EAFB. So this is equal to EFAB. Hence, this acts as an identity. Next, we want inverse for any A comma B in G. We have A inverse comma B inverse in G such that A inverse comma B inverse. This is equal to E comma F, and that is also equal to A inverse A comma B inverse B, and that is this. So it shows that this element is an inverse of this element. Hence, acts as an inverse of the chosen element A comma B. Now, there are some things that perhaps I should say more about here, about this calculation and about something else also, which is a little subtle and is often overlooked, is an inverse of A comma B. The purpose of doing all these extremely straightforward calculations is this. I want to first of all draw your attention to this simple fact. You see, sometimes what happens is that when we get used to these things, we become so fast that in our mind we forget to actually see whether what we are thinking is correct or not. Most of the times, because of the experience we have with these things, we end up doing the right thing, but sometimes we are wrong also. Nothing has gone wrong here. However, let's see how we are getting this from this. You see, we have taken any element A comma B in G, which is this Cartesian product. This means A belongs to A and B belongs to B. Because these are groups, so these elements have their respective inverses, which are also elements in this group. In these groups. And that is why this ordered pair belongs to G. So it's not simply that this directly implies this. Behind this implication, you actually have these things. And sometimes, like I was saying just now, if we entirely forget what is there in the background, then we may make mistakes. Now let's come to that subtle thing that I want to talk about. You may feel that here, instead of writing this line, hence this acts as an inverse of this, I could have just simply written A comma B inverse is equal to A inverse comma B inverse. But I don't want to do that. Let me show you why. You see, we are in the process of showing that the system is a group. Okay. Now we know that in a group, every element has a unique inverse. After proving that fact, when we started studying group theory for the first time, we proved this fact, right? Identity is unique, every element has a unique inverse. Then only we used this notation. G inverse is going to denote the inverse of the element G in a group. This notation comes only in a group, and because of the fact that there is exactly one such element which satisfies this equation. Now, because here, although the process is almost over of showing that our system is a group, but still, because I haven't finished writing that, so I don't want to use that notation yet. Only after having this much and knowing that yes, our system is a group, now only we know, after that fact has been verified fully, that identity is unique and every element has a unique inverse. Then only I start using this kind of notations. Now only I can write this. Not before that. Okay, it's not going to affect anything, but we should be sure of what we are doing. Oh, okay, so anyway, we have now completed showing that the operation that we have defined, which looks very simple and natural, indeed turns G into a group. So now G is a group, and this G, so G is a group under the above operation. It has a name also. We call G the external direct product of the groups A and B. A and B, okay, we maintain the order to indicate that G is A times B, not B times A. That would be another group. Actually, we will show ultimately that both of them are isomorphic to each other, but strictly speaking, that is another set, and so another group. And we call this product external because we have kind of constructed it using things. You see, why we are calling it external, that I think this will be more clear when we show something else, which is an internal product. An internal product as opposed to an external product. Let us recall something that we have already got. Do you remember that we have already seen something like this? Say H and K are two subgroups of a group G. We have already considered a product like this HK, and once we wanted to know when this HK is a subgroup, and it turned out that this itself is a subgroup if and only if HK is equal to KH. Now in this product, we have, in defining this product of two subgroups, we have used the binary operation that was already there in G. In that sense, this is an internal product. Here, however, we had to actually define a binary operation externally that turned the Cartesian product into a group. That's why we are calling it an external, the external direct product of A and B. Okay. But now we are going to see what kind of role do these groups A and B play in the group G. I mean, we have used A and B to construct G, so the group theoretic properties of A and B somehow are going, of course, they are going to affect what happens to G. But what kind of effect is that? In other words, we want to know how much of A and B we can find in G. It sounds a little strange because we have used only A and B to form G, so of course A and B determine G completely. That is fine. But once you have G, can you in some sense find copies of A and B inside G? It's like in the going in the other direction. You previously had A and B, you used them to form G. Now you have G, can you come back, or inside G itself, can you identify A and B? Can you identify the ingredients that were used to form the group G? So that is the next thing we are going to see. And for that, we are going to consider two subsets of G. Consider the following subsets of G. G means, of course, our G, A times B. external direct product. One of those subsets is we are going to denote it by A bar. Subsets of G, mind it. So the elements are going to be ordered pairs. This is one subset and another one such. Do not forget that this F is the identity element in the group capital D. That means we are considering those ordered pairs where the second coordinate is consistently the identity element in B. That is not changing, but we are changing the first coordinate and we are taking it to be any element in A. If you still want to look at this set in another way, it is actually nothing but this set itself is also a Cartesian product. It's the Cartesian product of A and the singleton set F. That's what it is. And the other set is B bar. You can almost guess what we are going to do here. Here for B bar, this component is going to be the identity element and we are going to free the other component. Free means we do not impose any restriction on it. So this is E comma B where B varies over B, and just like this one, this is the Cartesian product singleton set E times B. Because this set is somewhat like this set, only defined slightly differently. So let us first see something about this set. Okay, so this is a subset, right? This is a subset of what? G, capital G. G is A times B. Obviously this subset is non-empty. Why? That's because capital A is non-empty. So we are going to get elements ordered pairs like this. Clearly, this is a non-empty subset of capital G. What we are now going to observe is that this is not just a non-empty subset, but actually it's a subgroup of G, and not just that, it's a normal subgroup of G. Let's show this. Okay, so that means we have to now consider two elements and verify all the usual things. A1 comma F and A2 comma F belong to A bar. This means that A1 and A2 are elements of capital A. Then first we see what their product is. By the definition of our original product, this is A1, A2, FF. That is A1, A2, F, because F is the identity element. Because A1, A2 is again in capital A, so this belongs to A bar. And what if we consider the inverse of this? See, now I can write inverse because I already know that capital G is a group. Also, we already know what this inverse is. This is A1 inverse, F inverse. Since F is the identity element in capital B, A1 inverse F. But then again it has that same form, so it belongs to A bar. Hence, this is a subgroup of G. Next, we verify normality of this. So for that, let A comma B be any element in G. Then we have to form the conjugate of say this element by this element and see whether that conjugate belongs to A bar or not. Then let's do it on this side. You can either form A comma B times this times A comma B inverse, or you take the inverse first. Ultimately nothing is going to be different. You can do any one of the two things. Let me just consider this one. A1 BF, and this of course is A inverse B inverse. So this becomes A1 A inverse, and BF is B, and this B inverse we have with B. A1 A inverse is some element in capital A, and this is F, the identity element in capital B. So again this element, this ordered pair is of the form that we have in A bar. So we have this. Hence this is normal in G. Similarly, one can verify this, that B bar is a normal subgroup of G, and I leave this verification to you. Please do it, okay? Similarly, B bar is a normal subgroup of G. All right. Now we have not defined this A bar arbitrarily, just on whim. On whim we have not chosen this A bar. We will now show that this A bar is actually not just a normal subgroup of G, but is a subgroup which is isomorphic to the original A. Similarly, B bar is isomorphic to B, and that's how we will be able to find copies of A and B inside G itself. You can kind of see why that happens. This is what B bar is, right? So it's almost like B, and it turns out to be just like B. So they turn out to be isomorphic. Now, so we want an isomorphism, so we are going to define it. So just like everything so far has been very natural, so our function is also going to be very natural. We define the function phi from A into A bar, and our definition is just this. The image of the element small a, which of course is coming from capital A, is the ordered pair A comma F. You can clearly see that this is going to be an element in A bar. Moreover, for a given A, this is a unique element in A bar. So, this is well defined. Next, let us show that this is, we can write something else also. How do the elements of A bar look? The elements look like that. So, from the first coordinate, you can see that any such element is the output for a given input. I mean, if A comma F is any element in A bar, then that is the phi image of A. And that is why this function is clearly not just well defined but onto as well. Next, let us show that it's a homomorphism, group homomorphism. So let A1 and A2 be two elements in A. Then A1, A2 phi is A1, A2 comma F, but that is also A1, A2 FF, because F is the identity in capital B, and this is A1 comma F times A2 comma F, which is A1 phi times A2 phi. So this is the homomorphism. That means it's an onto homomorphism. So all that is left for us to prove is that this is one-to-one as well. So let's see what the kernel of this is. Let A belong to the kernel of phi. If you remember, we decided to use this notation to denote the kernel of a homomorphism. Then if you apply phi on it, it's going to give you the identity element in A bar, and that identity element in A bar is just the identity element in G, that is E comma F. So E comma F should be A phi. However, A phi by the definition of phi is A comma F. So from this equation we get A equal to E. That is why the kernel of phi is trivial. Proving that our function is one-to-one as well, besides being onto, and that's why it's an isomorphism of A onto A bar, proving that A and A bar are isomorphic. So phi is an onto isomorphism. In most of the group theory books, an isomorphism automatically means onto, but in this book, an isomorphism only means a one-to-one homomorphism. That's why we are separately saying onto. Hence, A bar is isomorphic to A. Similarly, and this is left to you, B bar is isomorphic to B. But something else is also true about this situation that we are yet to see. Let us take any element in G. We are now going to show that this element is the product of two elements, one from A bar and another from B bar in G. Note that this is also equal to A comma F times E comma B, because if you perform the product, you will get what? AE comma FB. which is nothing but A comma B, where the first element belongs to A bar and the second element belongs to B bar. This proves that any element in G is a product of an element of A bar and an element of B bar. So G is A bar B bar, and you know what this product is. This product is that product HK of two subgroups in a group, and in fact that's what it is. We have shown that G is equal to A bar B bar. But besides all these things, something else is also true. The representation of an element, any element in G, as a product of an element of A bar and an element of B bar actually is unique. That fact is also there. So let us next show that. Let C comma F belong to A bar and E comma D belong to B bar, such that their product is also A comma B. I need a little ink though. Now once we show this uniqueness, we can then go to the case where instead of having just two groups, we have any finite number of groups. And there of course we won't repeat anything, we will just simply mention that similar facts are true in that general case as well. One could also do all these things with the general finite case, but that just amounts to writing more things. Okay, it does not actually make it clear, rather it makes it somewhat messy and difficult to understand. That's why we are doing it first for only two groups, such that CF times ED is equal to A comma B. Then CF times ED is what? It's going to be CE comma FD, which ultimately is C comma D. And so C is equal to A and D is equal to B. Thus, the element CF in A bar is nothing but AF itself, and the element ED in B bar is nothing but the element EB, and that is why this representation of the element as a product of an element of A bar and an element of B bar is unique. There can be only one such representation. Okay. Now let us summarize what we have shown so far. In summary, G is the internal, we are just calling it internal, although we already have this product, right? You now understand why we are calling it internal. G is the internal product A bar, B bar of the subgroups, but not just subgroups, normal subgroups. Of the normal subgroups A bar and B bar, which are That too, these are not just any two normal subgroups, but they are related to A and B. In fact, they are isomorphic, which are respectively isomorphic to A and B. Also, any element G in G has a unique representation G equal to, let me write alpha beta, where alpha belongs to A bar and beta belongs to B bar. And now let us go to the general finite case. Let G1, G2 and so on Gn be groups. So in everything we write similarly in this general case is going to only be a remark about such things which can be proved if one wants. Let capital G be the Cartesian product of these groups in this order. For two elements and there is some kind of nocturnal bird outside. It's calling. And G1 prime, G2 prime, Gn, if you want you can name these things H1, H2 also, your wish. In G we define their product to be this. Where we understand that the individual products are in the respective groups. Gi prime has been calculated in G, capital Gi, using the binary operation that capital Gi has. Then this operation turns G into a group called the external direct product of these groups in this order. Now let us also define here similarly those subsets like A bar, B bar for any integer I in this range. We define Gi bar to be won't be able to write the tuple at one go, so I have to break it. Ei plus 1 En Gi belongs to Gi, where you do understand that these are the respective identity elements in the groups. So only the ith component we are leaving free. The others have been restricted to be the identity, just like there we put one component constantly the identity and left the other free. So here also we are doing a similar thing. Then Gi bar is a normal subgroup of G, that is isomorphic to Gi. Also, G is the internal product of these Gi's and every G belonging to G has a unique representation. G equal to what should I write? I can write anything actually. Say alpha 1, alpha 2 up to alpha n, where alpha I belongs to Gi bar for I varying from 1 through n. Okay, so we have come to know that if capital G is the external direct product of some groups, some finite number of groups, then G also turns out to be an internal product like this of what? Of some normal subgroups of G, and such that every element in G has a unique representation as a product of elements in those normal subgroups. Now, using this observation, we are going to define something else, okay, an internal direct product. So that is the next definition. With that definition, actually we are going to stop, but let's see what that thing is. Let G be a group and N1, N2, Nn be normal subgroups of G, such that two conditions are true. Number one, G is their product, ordinary product, and number two, see, the moment we say that G is their product, every element of G is has a representation as a product of elements of these subgroups. that is already there in this statement, but that uniqueness part is something extra. For that we have another condition. Existence of a representation of any element of G of this form already follows from here, but uniqueness does not. Number 2, for any G belonging to G, there exists unique I can call it Gi, say, belonging to Ni. I think in the text the author has written Ni, but it does not matter. For this such that G is their product. So we have a group and we have a finite number of normal subgroups that satisfy these two conditions. Then G is called the internal direct product of the normal subgroups Ni. So recalling the source of this definition, it's now clear that if capital A and B are two groups and G is their external direct product, then G is also the internal direct product of those A bar and B bar. Also, do not forget that whenever you try to verify that a given group is the internal direct product of some subgroups, those subgroups have to first be normal. Unfortunately, this is sometimes forgotten. Okay, we end up verifying just this condition and this condition and think that that's just it. But we have to first of all start with normal subgroups. And lastly, before I finish, there is a fact about finite abelian groups. Suppose you have a finite abelian group, then you have it's not the trivial group, but a group having order greater than 1. Then its order has a prime factorization. Say P1, P2, P3 up to PR be the distinct primes in that prime factorization. Then the group is going to have those Sylow subgroups corresponding to those primes, as P1 Sylow subgroup, a P2 Sylow subgroup, and so on. It turns out that G is the internal direct product of those Sylow subgroups. This is something that we will prove in exercise 5. So with that, I end my video tonight. So see you in the next upload, whenever that is. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.